menu was planned around beans, rice, wheat, sorghum, sweet potatoes, beets, and peanuts. Other vegetables and herbs brought much appreciated diversity and taste to the diet. Sweetness came from bananas, papayas, and other fruits. The Biosperians had to learn to cook without oil and limited ingredients.
You know, LEO's been underway experimentally for about 7 years now. And what's exciting today is that several of our researchers got some pretty profound grants, one from the National Science Foundation, actually two from the National Science Foundation, but one in particular is actually going to allow us to put plants on LEO. So the big studies up to this point have been looking at LEO in this current state, so relatively simple, what we refer to as a physical state, and how do the current hydrologic models predict the movement of water in this relatively simple landscape. But now when you add plants to it, how do those dynamics change? And that's what's really exciting, is that they're proposing to put alfalfa on these slopes, and they're going to look at how does that addition change everything that we previously observed. And so we're really excited. We've got a large team, some of which are international, that are going to descend on Biosphere 2, and we're looking at actually planting these slopes about a year from now. So there's a lot of preliminary work that will need to be done, and then we'll move into adding plants to LEO, which has been always a goal of ours, and now it will become a reality.
Is that the first time you've added plants to LEO?
It is. This will be the first time we've added plants to LEO, but if you look closely on the slope, you can sort of see some green patches. And so these are some mosses that have come in, sort of volunteered themselves onto the slope, and we see them on all three slopes. And we've got some folks at the University of Arizona who are looking closely at exactly what are those mosses and how are they interacting with the soil and what are they doing. So this is really exciting too, because it's a precursor to a more significant and substantial plant community on the slopes. You know, so the spores could have been present in the slopes themselves when we got the material from northern Arizona. They could have blown in, because we do run Biosphere 2 not only as a closed system, but oftentimes as an open system. That helps aid in the research that we're doing and the calculations that we try to do. And so some of those things could have blown in and sort of colonized these slopes, which is good for us actually. It provides a unique opportunity to carry out additional research. We have a number of international partnerships with institutions regardless of which biome you're in, but in particular, Leo, we've got a large partnership with the French, and so they have an equivalent to the National Science Foundation. They call it the CNRS over there, and so their Center for Research is collaborating with our teams to use this unique facility to address some of these questions that you just can't get at anywhere else in the world. Yeah, this space, we've transformed it. So originally it was the farm, the agricultural space, and then when the University of Arizona came in, we saw an opportunity to build a one-of-a-kind experiment inside of this large controlled environment to address a grand challenge, the fate of water in semi-arid environments. So it rains in the mountains. How much water ends up downstream for you and I to use? And as the landscape changes, how do those dynamics change? And the hydrologists will tell you that once it goes below the surface, we still know very little. Science has advanced significantly, but there is still so much more to learn. And water, in particular here in the Southwest, is such a valuable resource that we need to understand its dynamics and how to better predict its presence or absence. So it's predicted to run 3 to 5 years, and we'll see, and it will be very much dependent upon how the plants do, the type of data and results that we get out of it. And so I'm hoping it actually runs 5 years, because that means that we're getting a lot of really meaningful results out of these initial experiments. It's almost like a terraforming. They call it a GCR grant, but in simple terms, it's the National Science Foundation, and this particular is really looking at how we essentially terraform these slopes. So we're adding life in a significant way to alter the physical structures that make up these slopes. This summer we actually have a number of research experience for undergraduates who will be here participating in different aspects of that experiment, and so they will be doing a lot of work, and in turn we will be posting and interviewing, and they will be posting subsequent information, and we will continue to update, especially when we have intensive campaigns. So when we have some of our international partners here and other national partners on site, what we'll do is we will post on our social media oftentimes what is happening and why they're here and what they're doing. So we're inside Biosphere 2's rainforest, and it's probably one of the most unique and contrasting habitats that we have inside, coming from the Sonoran desert on the outside to sort of a lush tropical forest that you would otherwise think that you're in sort of in South America along the Amazon basin. That's exactly what it was modeled after, and this particular system has been the site of some really exciting research. So we had an international group of teams just prior to COVID hitting who came in and subjected our rainforest to a 70-day drought. And what they were looking for is to understand how the cycling of carbon, energy, and water changed as the system went from an unstressed to a very highly stressed state as a result of the lack of water. And so the lead researcher was from the University of Freiburg in Germany. Her name was Christiana Warner. We also had faculty at the University of Arizona led by Dr. Laura Meredith. And they led this team, and I believe there were about 15 different international institutions. We had a total of probably close to 80 researchers that came and went for this particular project. And you can see some of the tubes still in place where we're still doing some of the monitoring. We have overhead structures where we actually had students up in the canopy taking long-term measurements, and those results were actually just published in Science. And so you can actually go to our website, we've posted it, and it was called the Wald experiment, which is Wald in German, which means forest, but it was water, air, life dynamics. And it was a really exciting experiment, and I think exemplifies the power of Biosphere 2 as a user facility to do experiments that you just couldn't do anywhere else in the world. And the really unique opportunity is we gain insight into how these systems may respond to future climate change. The system was very stressed. I mean, what we want to do, part of it is the experiment actually had to stop a little bit early because of COVID, and a lot of our international partners needed to get back to their home country because travel restrictions were either going to be or shortly going to be imposed. But also the system was really stressed. It did not look like it does today. I mean, all the plants were wilted. You could tell for the most part that it was under severe stress. But you know, these are the types of things and events that we see happening in a lot of these regions. And so we try to use models to predict what the behavior will be in the future. But the data that we put into the models is only as good as that which we have. And so Biosphere 2 helps to refine that. And that's what's exciting. So the data that you put in and your models are only as good as that data. This location in particular helps with model validation and calibration. And so with Biosphere 2, it's a unique tool that complements what people are doing in the lab and what people are observing in the field. We're sort of this intermediate step. We were cautious. We monitored the system when we had a number of folks who had varying degrees of expertise to ensure that we didn't push the system, as they say, over that proverbial cliff. But we wanted to stress and push the system. So after the drought, everything responded surprisingly well and recovered. But the one thing you'll notice is that we don't have much in sort of this what I call a mid-canopy area. We got a lot of stuff overhead, a lot of stuff under. We don't have anything in this mid-canopy. So one of the things we initiated after the drought, and this was not the result of the drought, it was just over the 30 years of Biosphere 2 being in existence, is our team, and primarily led by Jason DeLue, has added about 100 new trees to this lowland area. So he's added things like coffee and cacao. So we know cacao is a primary component in chocolate, or the component in chocolate. And so we've added them, and we're hoping what we'll see in the next year or so is we'll fill in this mid-canopy gap with these agroforestry trees and products. And so that was a crucial piece, and it's one of the things that you have to continuously do when you have a facility that's been around as long as Biosphere 2. Inevitably, certain plants are going to reach the end of their life, or they're going to die off, and you're going to have to add them back in to maintain diversity. But today, we still have over 100 species inside Biosphere 2, it's rainforest. It was attributed to shading. Some of it was just end of life with certain species, and now this is the sort of the next generation coming up. And Jason, actually, we carefully selected all of the plants. They were all grown from seed and then transplanted inside of here. There are very few animals inside Biosphere 2. So there are a few birds, there are a few reptiles, a few amphibians, but mostly what you're going to see, regardless of whether you're in the rainforest or other parts of Biosphere 2, is an ant. It was accidentally introduced in the very beginning. It's called a crazy ant, and it's a dominant insect inside. But if you come in at night, you're going to see a lot of roaches, and there's 3 different types of roaches, which oftentimes people sort of get a little bit squeamish about. But roaches were intentionally introduced, and they were extremely important because they help with the breakdown process. So we don't add fertilizer to our systems. So everything that you find inside is dependent upon what resources they get from inside. We don't add them in. So that's a critical component to recycling the nutrients and being able for these plants to reuse it and continue their growth cycle. So we hear a lot about the microbiome and the human internal organs and the guts and how important it is. But likewise, it's equally as important in a lot of these ecosystems, and we're finding that the microbiome is actually the driver of a lot of these sort of larger processes. And so that's what's exciting. And with Biosphere 2, you can really sort of focus in almost thread by thread what those microorganisms are and what they're doing and how they're responding to these environmental changes. So the temperature in here right now is about 92 and the humidity is about 95. We had a group of students who came in and surveyed the mangrove system. So this was part of Ecology 482. So this is an ichthyology class at the university. And Dr. Peter Reinthal is the professor for it. He's been teaching it forever. He's sort of the foremost southwestern expert in these small endangered fish. But what he did is he brought the students in and they did a mark, capture, recapture experiment. So they did a mark recapture experiment in our ocean system, or in our mangrove system. And so we have a small fish that lives in there. And so what he was able to do is the students set traps on one day, and then they would come back and check the traps, and they would mark the fish by clipping their tail. They would release them, and then they set the traps again, and another group of students come back and check those traps. And what they can do is, based on the new individuals they caught versus the ones that were previously marked that they recaptured, they can assess and determine what the population is. And so what we're going to do is this class will come out regularly and do this over the coming years to see how our population fluctuates inside. So we're seeing much greater engagement with the undergraduates at the University of Arizona. We've got another group of students that are going to come out and they're going to test sort of how certain natural products do in the different biomes. So they're going to set some things up in the desert, in the savanna, in the rainforest. We've got students who are measuring photosynthesis. We've got a capstone engineering team that's developing a device that will measure methane that will float. So as these areas in the rainforest are flooded, this device will rise and fall accordingly. But they're going to first test it in our rainforest, and they're going to do that here in about a month. And so we've got a section of the rainforest that's called a varzea. So this means a seasonally flooded plain. So there's a small stream that runs through it. We can flood that. And so they're going to flood it just like what would happen in the Amazon. They're going to test this instrumentation, hopefully work out any of the bugs before you go down to the Amazon basin and deploy it. The ocean is an amazing system. I mean, it's 1 million gallons. It's the world's largest research tank. It's not the world's largest tank, but all of the research that we do here at Biosphere 2, we want to push these systems to understand how they're going to respond to future climate change events. And in our ocean system, we have a unique opportunity to test novel ideas and novel coral species and how they're going to respond, in particular to changes in temperature in the future. So, for example, 50% of the Great Barrier Reef has been lost or bleached, most of which is attributed to these very dramatic increases in temperature. But there are always individuals that survive those events, and so there is a group of researchers who want to know, can we selectively breed for those individuals, basically favor those traits so that we give reefs an opportunity and hopefully the ability to survive these future conditions that we predict are coming. And so there are researchers who say that at the current rate of loss, by 2050, reefs as we know them could cease to exist unless we do something very dramatically. And so Biosphere 2 offers an opportunity, basically, so those things that you're first afraid to do in nature, you can do inside Biosphere 2 because it is a controlled environment. But we have an exciting project. What we're going to be doing is we're going to be adding trusses over our ocean. We're going to be suspending lights, and that is important for corals to grow. And then from there, what we can do is we can ensure we have a very consistent water chemistry, a consistent light level, and then we're going to change the temperature. And we're working with groups, for example, in Mote Marine in Florida, to test new varieties of corals that show greater resiliency. Get them to regenerate faster, regenerate areas that have currently lost their corals and they're all completely dead. Yeah, there's a number of different techniques, and so we hope to be able to work and test these novel techniques in Biosphere 2, because a lot of times there's many institutions that are not going to allow you to introduce a hybridized coral inside or outside in the open environment. You need to run a series of tests first, and this is a great place to do that because we have a complex system. It's more complex than your typical aquarium, but we have much tighter control, and we're willing to push the limits of the system. But in addition to the corals, we've got some folks over in behavioral and social sciences at the University of Arizona. And one of these team members and his collaborators, his name is Wynn Burleson, but he's collaborating with a private individual. His name is Mike Bombardier. And what he does is he's developed an inflatable envelope that then divers can actually stage themselves in. And it was recently featured on Shark Week because what they did is they suspended it. Divers could go in, they could still observe out. But then as soon as these great hammerhead sharks came into the area, they could deploy themselves, and I guess they're very skittish and shy, And so going in and out of the water was not an option, but this allowed them to go stage themselves at the depth and observe it. And what we're going to be doing is he is actually going to be deploying this next week here inside of our ocean, and they're going to do some long-term testing and having people stay in it, not just for a couple of hours, 4 or 5 hours, but looking at 24 to 48 hours and sort of what's the physiological response, how do people do, how do you interact with it. And so this is another great place to test sort of those novel ideas in a very highly controlled environment, but also we've got the public that comes by. So we have an opportunity to explain what we're doing real time to those visitors that are here on that day. So one of the things we've been looking to do over the past several years, and really this is primarily the result of all of the hard effort, not only the entire team, but in particular a gentleman by the name of Jason DeLue. He's our terrestrial biome manager. But what he's done is he's looked at sort of restoring a lot of Biosphere 2's areas to their original state or enhancing them. And this is one area that he's enhancing. So what he's done is all of these plants were grown from seed, and then he transplanted them in here to establish sort of a little agroforestry area. But what we have is, this is an avocado plant here. We have coffee, we have papaya, and so he's added them in, and this area will eventually grow up. And you can see the papaya is fruiting right now, and a lot of these others we hope over time will also fruit. But we're excited to continue to improve and enhance the vegetation inside Biosphere 2, because again, you know, when you have a facility that's over 30 years old, there are a number of plant species that eventually reach the end of their life cycle, and so you've got to add new ones back in. And so this is one of those initiatives in an area that didn't have a lot of use, has had some experiments go on, but we thought this would be a great opportunity to add some of these plants that people consume regularly, but oftentimes don't get to see in situ. Much like we've added plants to our rainforest, to our lower savanna area, again, we've made a concerted effort to repopulate and revitalize our desert system. And so a lot of the plants that were originally incorporated into this coastal fog desert had been lost over the years, and so we've made an effort over the last couple of years, led again by Jason DeLue, our terrestrial systems manager, to add in a lot of new plants. And so you can see them all up in these areas here and throughout. And we've got plans for the future of actually adding a small stream in here with flowing water. And then we're working with one of the ichthyologists, a guy who studies fish at the University of Arizona, to potentially create a habitat for some of these endangered fish species, so the pupfish and the long-finned dace and some of these others. So we're looking at doing that, and hopefully we'll be able to realize that project within the next year or so. The stream would start up here, it would come down, and we would have a pond down here, and so we'd have some pools along the way as staging points for the fish. And then it would also serve as an educational opportunity, because there are several ecology classes that focus on fish and fish ecology that would use the class throughout their semester as a study component or as a lab component. So it offers and is complementary to field research as well, in a sort of a unique setting. is we had to adapt in the face of COVID, and we had to adjust and change our model and the way in which we presented our content to comply not only with the national standards, but also with the standards that the University of Arizona had in the face of COVID. And for us, that meant moving away from sort of guided tours, which was what we historically did, into an app-based tour. So now you can experience Biosphere 2 at your own pace using the Biosphere 2 Experience app. You can download it on Google Play or the Apple App Store. You don't have to be on site to actually go through and listen to the content. You could be elsewhere. But obviously being immersed in these systems adds an extreme component, I think, to the tour itself. And you can dive as shallow or as deep in a lot of the subject matter. And so we have not only present footage, but we also have archival footage as well that you'll be able to access. So you can listen to and hear some of the original Biosphereans, see some of the footage of what it was like when they were going in or eating a meal inside or their apartment. And so we think it is very complimentary, and many folks who visit today, I say with the overwhelming majority of people, really enjoy the app ability and the experience itself.
What we're standing in front of is it's called the test module. It was the 1987 prototype. It was the second prototype. The first prototype became the gift shop. So this was the second prototype at building a hermetically sealed pressurized vessel. And as you can recognize, a lot of the architecture, the space frame, the stainless steel floor, the way that the windows are sealed is nearly identical to the way that the Biosphere 2 over there was actually built in the end. So this was the functional prototype, and it operated for about 3 years with individual Biosphereans staying inside. And at that time it was filled with plants, and it will again be filled with plants, such that all of their air, all of their water was completely recycled by the plants with no need for machines. And their food came from those plants as well. So the record stay was by Linda Lay, who's one of the original Biosphereans, and she lives in Oracle now. And she was inside for 3 weeks without any outside food or air or water, which is a pretty incredible accomplishment for just 400 square feet of space. But she demonstrated that there is a long-term sustainability within that bioregenerative space. Our project is called SAM. It's a space analog for the Moon and Mars. So we started with this historic building, and we refurbished this building last year from January through June. So in about 5.5 months, we were every day out here scooping up 30 years of debris from, the desert likes to move in, and so we had to we had to use jackhammers and grinding wheels and cutting wheels and take everything out that was in there. Some of the original materials, some things that had been used in the meantime for interim experiments, and we completely cleaned and washed and repainted the entire facility and got it sealed and running again. So we were able to use some of the original equipment, and it was fully pressurized as of June, just this building here. And now we're in the process of adding on the crew quarters. So this 20-foot shipping container and the 40-foot shipping container, and just as of yesterday, we added the airlock on the end. This now extends the pressure vessel so that we have the capacity to have a greenhouse coupled with a workshop, coupled with a living space for the crew. And the crew that will be coming through, there'll be research teams from all over the world who will rotate through every couple weeks or every few months. The shortest stay would be 5 days. The longest stay could be 5 or 6 months without leaving that pressurized space. Most of the experiments are in food ecology, plant biology, in food cultivars, chemistry. There's some radiation studies, just looking at different means of mitigating natural radiation. And a lot of the studies are some of it's psychology studies. If NASA comes, for instance, they will be certainly doing long-term psychology studies. How do you handle crew dynamics, and how do you deal with or mitigate any kind of confrontation or issues between the crew members when you're inside a very, very small vessel and for a long period of time. So we would anticipate that NASA, if they bring a team, they would stay inside for anywhere from 2 to 3 months would be their goal. No, we actually have a mission control center, which is in the lower parking lot. We're building that out. So there's actually a number of analogs running around the world today. There's one in Hawaii, there's one in Utah, there's one in Poland, there's one in South America, they're all over. There's one in Russia called Sirius, one in Antarctica, and those analogs each have their own area of expertise, but we will be the second sealed analog in operation today. The first one that's sealed right now is in Russia, in Moscow, called Sirius. There is a sealed vessel at NASA Johnson Space Center, but it's not used on a regular basis anymore, and it's just a big metal can, essentially. They call it the can. So this will be what we consider to be the highest fidelity and the closest approximation to what might be a second or third generation habitat on Mars. So the first habitats on Mars will essentially be the volume of a shipping container. It's going to be a rocket fuselage and maybe an inflatable habitat next to that. But as we bring more and more vehicles to Mars, we're able to bring extra equipment, extra gear, and extra facilities. We hope to be able to expand on those facilities and have more of a permanent established residence. So this represents what we call a second, third, or maybe fourth generation habitat. So it's beyond that first spacecraft, but it's not a full city. Everything from Gemini all the way up through Apollo and the Space Shuttle era, it was just NASA contracting out to commercial companies in order to assist. But now we have commercial companies leading the way. We have SpaceX and Blue Origin and Virgin Galactic and Sierra Space. They're now, yes, they're still getting funding from NASA, but they're leading the way and they have their own objectives and their own missions, and that's the difference, is that typically the government has the money but not the courage. And so the private companies have the courage but don't have the money. And when I mean courage, I don't mean that NASA shies away from it, but that they're very, very risk adverse when it comes to human exploration. And I think too risk adverse. I mean, driving in your car in a city is far, far riskier than going to Mars. But if somebody is injured on that trip to Mars, the whole program's shut down. We do have direct relationships with some of the aerospace companies today. And we have, in fact, we already have agreements with some of them to bring some of their facilities in and do testing here. One of those is Paragon Space Development Corporation out of Tucson, which was founded, of course, by Tabor and Jane and Grant Anderson. And they've just received a $100 million a grant from NASA to perform some exceptional work. I mean, they've been building up for years, and they're really, really coming into their own. So this is the airlock. We just installed this yesterday. So this was originally in the basement of Biosphere 2. It's one of the original airlocks or secondary airlocks. So it's at least a 25, maybe a 30-year-old structure. So we just moved this over with a massive forklift yesterday, and we attached it to the side of our ship, what will be the crew quarters. Very much just getting going on we haven't worked on the interior space. Right now this is our storage unit and our workshop, as well as what will be the crew quarters. So the airlock there will be a pressure door here as well to form a proper airlock. Right now it's just a sealed exterior door. So to function as an airlock, because we're not moving in and out of a vacuum, to simulate that, there'll be a pressure door on this interface. The crew will enter the airlock, seal the pressure door behind them, and then we'll pass a certain quantity of air through the airlock to represent the compression or decompression of the airlock, and then they'll exit into the Mars yard. And so opposite us on the blue tape, this represents the door that will go into the 20-foot container. So this will be the living space. Behind you will be the bathroom. And so there'll be a toilet and a sink, and ultimately even human waste will be fully recycled. But we're going to take it step by step. The technology is there, but we also have to comply with county regulations. So initially it'll be an RV style toilet where we'll actually capture and take that waste away, but ultimately we'll be working into a fully recycled system over the course of the next 2 years. If you put it under a shade structure, it can work very, very well, but I don't agree with putting steel containers directly in the sun. That doesn't make sense to me. There should be a shade structure to block it, or at least coat the thing in pure white. So the number one thing all of us can be doing right now to mitigate climate change, number one thing is paint our roofs white. It's the number one thing. Eat less meat and paint our roofs white. If everyone ate half as much meat and painted the roofs white, we could reverse climate change almost overnight. I'm exaggerating to some degree, but people don't understand how simple it is to mitigate a lot of what we're doing. A lot of what we're doing in SAM, yes, we're talking about the pretense of going to Mars, and that's the exciting part. But what people may not recognize until they live in here is what we're really doing is training people on how to live on Earth. Right? We should all be eating less meat or even vegetarian, and that's not a religious statement, it's a fact as to how we use our land and how much resources we consume. The second thing is complete and total recycling. There is no way, there will not be a single waste basket in this facility. I don't care if you're in here for 5 days or for 5 months, there are no waste baskets, there is no place to throw away. There's no packaging. All of your clothes should be organic clothing, not synthetic clothing, something you can repair. And all of your food has to be completely regenerated. Now, granted, that space in our greenhouse is not big enough to supply food for 4 people, so we will be augmenting that or that I should say that is an augmentation for this. But the food that we will supply for the crews inside is completely dehydrated, dried, or freeze-dried foods. And so people have to learn how to cook in a very different way than what they're used to. They can't just run down to the grocery store every day. So our team will be performing all the tests in advance of the first research teams to arrive. We have to make certain that the air is fully recycled and that the oxygen content is high and that the CO2 level is low. There's other kinds of chemicals that build up both in the water and in the air that we have to be very cognitive of. It's not as simple as just removing this and adding this. There's different kinds of alkaloids and different chemicals that build up that we're not even aware of because our larger Biosphere 1 mitigates that, and except we now recognize that we've reached the limit of that buffer. You know, we've reached the limit of Earth's buffer and we're starting to see the consequences. So in here, those buffers are much smaller and will happen much faster. If you don't properly manage the air quality or the water quality, you'll know within 48 hours. If you've done something wrong. We just did this in just one afternoon, one day. We got this cut out, so the next is that one, and then we keep going in terms of framing in the end and framing in this end. So we're looking at about hoping 4 to 6 weeks to have the entire pressure vessel resealed. Wow. So that we can repressurize the entire thing, in which case all the air is trapped inside and we're at a slightly above ambient pressure. We try to be about 1/10 of 1 psi over ambient so that we can claim a hermetic seal, which means that there'll be no biological contamination coming in from the outside, and any leaks, because there's always leaks, will be to the outside. If we're doing microbiome studies, for instance, we don't want open windows. We don't want a constant flow of air. Now, that said, the teams that work and do research here will have a choice as to what level of fidelity they want to come in at. So some of the teams will just want natural airflow. That means that, it doesn't mean you open a window, it means that the air is quantified. So we will bring in a certain quantity of air per day, and that will be part of the scientific experiment that we measure that quantity of air. And other teams will want this to be open, but the greenhouse to be sealed. And other teams will want the full fidelity where the entire complex is sealed, and when they're inside, that's it. And we also have 2 full spacesuits, full functional spacesuits. And when you exit to go into the Mars yard, you'll be wearing a full spacesuit with an umbilical cord, and all of your air and everything is from within this breathable space. So you have to picture within this space, you're standing with your back to the bathroom. Right. This is the hallway that takes you into the 20-footer. The kitchen is here, the common area is there, and at the very end, there'll be 4 sleeping lofts, or four cots for the people to sleep, for the researchers, up to 4 people. That doorway down there is going to be completely sealed. Those doors come off. We frame that in. There will be an emergency exit on the end, simply to meet county fire codes, to make certain that if there's a fire or something bad, people can just leave. We'd rather have somebody get out okay than and ruin the experiment than ruin themselves. So. We have about 6 teams ready to go. Well, the number 1 is Jane and Tabor, who are the original 2 of the original Biospherians. So they will hopefully be the first team besides our core team to come and stay for a couple of days. Myself and Trent Tresh and John Adams and Colleen Cooley and Sean Gellenbach, and we have a wonderful array. We had 12 researchers last year. We've all played our part. So when I say I did, I mean as the director, I've motivated it, but it's really the input from all the team members and a lot of time drawing and sketching and revising and researching and reading about all the other analogs and all the historic missions that NASA has performed. We also have direct guidance from a number of people at NASA. So we have the director of the Humans to Mars project. We've got the folks who are at NASA Johnson Space Center who are designing the Mars habitats now. They're influencing our decisions. We reach out to them when we have critical decision points. So this is really a very, very large collaboration. We have a working group of about 65 people that are involved weekly or monthly. We have a lot of activities where you can try on a spacesuit and you can try geology, and we have basically a reduced gravity rig. It's called a gravity offset rig, where you can harness yourself to a cable and experience lower gravity fields and such. I actually post every week. I post not on the Biosphere 2 website directly. You can start there, and under the research drop-down, there's a sub-menu for the Mars habitat. Okay. But if you just go to SAM-B2, S-A-M, the letter B, the number 2, .space, and then there's a blog, and every week I post stories, photo essays, and videos of everything we've done. There's over 1,000 photographs and about 75 stories so far. And they're traditional long format, not just little social media blurbs. They're traditional long format stories that people really enjoy, because we mix science with, physics with mechanical engineering, with all the challenges of getting our hands dirty and breathing dust and everything that's taken to do this. So it's a fun read. So this is the pressure seal to the original 1987, 1987 test module. Again, this is still in a state of construction, of course, but you can see the original stainless steel floors, which are fully airtight and watertight. The entire Biosphere 2 has 3.1 acres of stainless steel floor. Every single square inch of that building, including under the rainforest, under the ocean, is all stainless steel. I mean, think about the cost today to do this and how much welding it took. 3.1 acres of stainless steel. You have to have stainless steel. So we have new air conditioning systems, we've tinted the windows, so the amount of light in here is 50% less than what would be outside, which takes us closer to approximation of what it would be like to be on Mars. Mars is further away from the sun, therefore it receives less light. So that's the lung, that's how we pressurize the test module. We can look in there in just a moment. This isn't finished, but this is the interface between the test module and the first 20-foot shipping container. And so that'll be the port, there'll be steps that go up, and that's actually how you get through. So this will be filled with hydroponics growing racks and grow beds. We've got 6 racks on order, and those racks should arrive in about a week or 2, and then we'll be building out those racks. So there'll be 6 hydroponic systems in here, a small grow bed and research facilities and such, so that we have a lot of plants. We'll be hanging algae bags from the ceiling. And
do you have to keep the humidity level a certain range for all
the plants do prefer a higher humidity than we do. We can coexist as they did in the Biosphere at that higher humidity, but ideally for mold and mildew, we want the crew quarters to be at a lower humidity, and for the plants, we want this to be at a higher humidity, depending on which plants we're growing. But most food cultivars prefer a slightly higher humidity. So this is the lung, and the lung is a very interesting example of really basic physics. So this is a 3,800-pound steel plate, and the outside of the steel plate is secured to the outside of the lung with a rubber membrane, so there's a flexible membrane. So it's basically like a speaker head on a speaker driver. And so that plate is able to float on a cushion of air. Underneath us is a tunnel that goes into the test module and by extension into our new expanded air crew quarters and such. So when we turn on the blower, we'll be inflating this like a balloon. And so this will inflate, then we turn off the blower and seal it up, and that weight of the steel is pushing down on the column of air beneath it and applying a positive pressure. That positive pressure then extends under where you're standing into the space, and that's how we maintain, with no machinery, once we turn off the blower and we shut the valve, we have a positive pressure inside with no moving parts, and gravity's doing all the work. And so the beauty of that is that it's an older style analog means of maintaining pressure, which means it's reduced failure because it's reduced moving parts. Now, in addition to that, we will have a mechanical system that was designed by an undergraduate capstone team last year that has a Raspberry Pi computer and has pressure valves and has a compressor and has storage tanks. We'll also have that in addition to this to maintain the positive pressure inside this atmosphere, inside this environment. That's one of the experiments we want to conduct, is which one works better, which one responds faster, which one can we trust more, a gravity-fed system or a mechanical system with computers and moving parts. We have about 5 areas of research that we're doing ourselves in addition to, or as a foundation to, and the teams that come in can play off of and build off of our experiments, or they can bring their own experiments in. There's unlimited types of experiments that can be done here. So this is literally the hardest effort. We've put more time into here than anywhere else, just because it wasn't designed to last 30 years. The roof was leaking and there had been rust in there, and this is filled up with water, and so we've still got to finish painting and priming the bottom now that we have it all watertight again.